Hello everyone, let's solve a problem from GATE 2019, question number 36 from Aerospace Engineering paper. A two-dimensional incompressible fluid flow is described by the stream function psi is equal to xy cube meter square per second on a Cartesian xy plane. So if the density and the dynamic viscosity of the fluid are 1 kg per meter cube and 0.1 kg per meter second respectively, the magnitude of the pressure gradient in the x direction at x is equal to 1 meter and y is equal to 1 meter is dash Newton per meter cube. So we have been given a stream function. From that we can find the velocity components in x and y direction. It's a two-dimensional flow, and let's apply the incompressible Navier-Stokes equation and then try to find the pressure gradient in the x direction. For that it's sufficient to use only the x momentum equation, right? Let's go and do that. First, before that, let's find the velocity components in x and y direction. The psi is given by xy cube, right? So the velocity component is in x direction is given by u. U is dou psi by dou y. Okay, so if we differentiate this with respect to y, then we will get 3xy square. So v is equal to minus dou psi by dou x. So if we differentiate psi with respect to x, then we will get minus y cube, right? And what else is given? We have to find the pressure gradient when the fluid density is 1 meter cube, 1 kg per meter cube, and the dynamic viscosity is 0.1, and dynamic viscosity is 0.1 kg per meter second, and pressure gradient dou p by dou x at x is equal to 1, y is equal to 1 is what? This is the question, right? For that it's enough here to use the x momentum equation alone, right? So let's write the x momentum equation. Rho into dou u by dou t, unsteady term, then the convective term will get u dou u by dou x plus v dou u by dou y equal to minus dou p by dou x plus u into dou square u by dou x square plus dou square u by dou y square, and neglecting all the body force we will get this equation, right? So from this we just need to find the pressure gradient, right? So if we just write the pressure gradient in the left hand side, we will get mu dou square u by dou x square plus dou square u by dou y square minus rho into dou u by dou t plus u dou u by dou x plus v dou u by dou y. So let's find the derivatives here. So we have u as 3xy square and v as minus y cube. So we need a derivative of u in x and y. Dou u by dou x is 3y square, okay, and then dou square u by dou x square is 0, right? And then dou u by dou y is 2y. We will get, if we differentiate this, we will get 2y, and we also have 3x, then we will get 6x y, right, 6xy, and then dou square u by dou y will get 6x, right? So then what else do we need? And then we don't have any variation with respect to time. It's a steady flow, so this term will vanish, right? Now let's just substitute. We'll get mu is 0.1, right? and this also we have to substitute at 1, right? So at 1 comma 1 we will get dou u by dou x as 3, dou square u by dou x square is 0, dou u by dou y is 6, dou square u by dou y square is 6, and u is 3 and v is minus 1, right? Dou square u by dou x square is 0, dou square u by dou y square is 6, right? Minus rho is 1, u is 3, dou u by dou x is again 3, plus v is minus 0.1, right? So dou u by dou y is given by 6, right? So we get 0.6 minus 9 minus 0.6. Sorry, this is minus 1, so we get minus 6, right? So so this minus and minus will get plus, so we'll get 0.6 3 minus 2.4 Newton per meter square. Since we have been asked to get only the magnitude, so we will just take 2.4 as our answer. Okay, so that's all for this question. If you want to know more about similar concepts, so you can refer to the NPTEL course Advanced Concepts in Fluid Mechanics by Professor Suman Chakrabarti from IIT Kharagpur. You can also refer to the lecture from week number 12, lecture number 16, which is Navier-Stokes equation. You can also see the YouTube link for that particular lecture here. So that's all for this question. Thank you.